Hello! Today we are going to talk about fiber optics, or at least what you need to know as an electronics technician about fiber optics. So what I'm going to try to do here is take my 1-week seminar about fiber optics and compress it down into a video that tells you what you need to know as an electronics technician. So let's get going. Just a reminder, these videos are lectures for my free course in electronics technology that you can take at Vocademy.net. You can find the reading material there, and if you create an account, you can take exams and track your progress, and will be notified when I put up new video lectures, among other things. So just go to Vocademy.net and sign up. It's 100% free. First of all, let's take a look at why we use fiber optics in the first place. So I'm going to have to step a little bit into the communications class, so I'm going to get a little ahead of myself here. But when it comes to how much data or information you can carry through a channel, whether it's data or voice or whatever, the frequency of the carrier has a very large effect on the speed of the data that can be sent through. And this is what we call bandwidth. So I'm going to step a little bit ahead of our class here and talk about that. So let's say we're talking about AM radio. And AM radio has a typical carrier frequency of around 1 megahertz. So I'm going to draw that as a vertical line here. So there's our 1 megahertz. And the practical bandwidth at 1 megahertz is about 10 kilohertz. So it's not a really wide bandwidth. And what I mean by that is, when we have this carrier, which is just a simple sine wave being sent to an antenna, and we have a current going up and down that antenna which disturbs the equilibrium of the space-time continuum and causes electromagnetic waves to radiate away from that antenna. And the power profile of those electromagnetic waves is a sine wave. So in other words, it goes up smoothly and down smoothly in power as time goes by. And we've already seen this shape in AC electronics, so know all about what this sine wave means. So it's a pure frequency of 1 megahertz. But now we want it to carry some information, so what are we going to do? We could turn it on and off and use Morse code, or we could amplitude modulate it, making it stronger and weaker, varying according to the information we want to send. So for voice, if I pretend this is a microphone, there's a diaphragm inside that moves away and close in synchrony with the sound coming from my mouth, and that produces electric waves which we send to the modulator, which causes the power of our transmitter to get larger and smaller according to what this diaphragm is doing. So as it gets closer to me, the power becomes less. As it gets further away, the power becomes more, and we get this power profile where our power, let me see if I can give a drawing of this, coming out of our transmitter is greater, lesser, greater, and lesser. And this is what's called amplitude modulation. Or we could vary the frequency. There are different ways we can go about carrying information. But what that does, anytime we modify that sine wave, remember back into the AC class, if we have anything other than a sine wave, what do we get? We get more frequencies. So remember that with a square wave, turning it on and off, we end up with the fundamental frequency plus all of the odd harmonics are mixed in with that. And we talked about that previously. I don't want to go into more details. You can review about the wave shapes in the AC class if you want to remember more. And we'll talk more about this in the communications class because it's important there. So we get more and more frequencies. So what do we get? We start out with the sine wave, and as we modulate it, we get frequencies above the frequency of the sine wave, and we get frequencies below the frequency of the sine wave. And lo and behold, that's what we call our bandwidth. So to carry that information, we need a wider range of frequencies than just one. And if we take away these sidebands, as they're called, the information's gone. So we must have a wide range of frequencies to carry that information. Well, once again, at AM radio frequencies, we have a bandwidth of approximately 10 kilohertz. Now, I'm sure that we can get a little more than that. I've tried to look up what the math is about that and can't get a satisfactory answer, but basically what is standard at this frequency is about a 10 kilohertz bandwidth. And so if I'm talking, I'm producing frequencies up to 20 kilohertz. And so we're not going to get a very good approximation of my voice at AM radio. We're going to lose a lot of the higher frequencies because the 10 kilohertz bandwidth cannot carry those higher frequencies that go above the carrier and go below the carrier. But now let's change that to FM, where our typical carrier is 100 megahertz. Now our bandwidth gets a lot wider to be about 200 kilohertz. Well, that's way more than enough to carry the human voice. In fact, on FM radio, we can carry 2 channels of stereo music at high fidelity with the music sounds going up to 15 kilohertz, and we still have room left over to carry other information such as, they used to use it for pager signals, elevator music, all sorts of stuff. I don't know if it's still done, but that used to be incorporated into FM radio because we had all this bandwidth to play with. So at the higher frequency, we have a greater bandwidth. Okay, now if we keep raising that frequency, we can have a greater usable bandwidth. So now we're talking about radio. What is light? Light is the same thing as radio waves, just much, much higher frequencies. At the frequencies, or should I say the wavelengths used in fiber optics, remember wavelength and frequency are the reciprocals of each other, we're talking about 100 terahertz of our carrier frequency. So our bandwidth is absolutely tremendous. What does that mean? We can carry very, very, very high-speed data if we use light as our carrier. And so what do fiber optics do? They carry light. So just by using fiber optics, we're already giving us a tremendous bandwidth, a tremendous speed of data that we can send down that fiber optic channel. So that's number one. Number two is distance. Now, up until around the 1960s, no one knew how to make pure enough glass that we would not lose signal over a fairly short distance. But by using ultra pure glass made of silicon oxides and germanium oxides, which we can control the ratios of those to produce certain properties, we learned how to make glass that was so transparent that it could carry these light signals for tremendous distances. And there are other things that limit the distance that the light can go, but we will talk about that in a moment. So now we have light that can carry very high frequencies, and now we can make glass that can carry that signal through glass for very long distances. So it can carry much greater bandwidth, in other words, data speed or frequency range, and it can carry it for a much greater distance in, say, coaxial cable or something, because the attenuation going down copper cables is much more than modern fiber optics. So the advantages of fiber optics are that they can carry high-speed data over long distances, and they are immune to electromagnetic interference. So data sent over copper wires can pick up electromagnetic interference where fiber optics can't. Fiber optics are lighter, thinner, and more flexible than copper wires. And theoretically, they're tap resistant. You can't tap into a fiber optic and steal the signals, although you can actually do that. If you bend a fiber optic enough, some of the light will leak out and you can pick up signals. So it's not really true that they're tap resistant. They can be tapped fairly easily if you can get to the fiber. But one thing you can't do with fiber optics is pick up radio signals that are emitted from the wire. So data cabling in buildings using copper is sending out all sorts of radio signals, and yes, people have picked these up in industrial espionage. Industrial espionage does happen. I've seen it happen. So data could be stolen with the right equipment when you have copper, but with fiber optics, you do have to get right up to the fiber if you do want to tap it, although it can be done. And theoretically, some modern installations of fiber can actually be less expensive than copper, although I find that a dubious claim. I'll have to look at the numbers and see if they really can be cheaper, because typically fiber optic stuff, the equipment, everything tends to be more expensive than what you would use with copper, which brings us to the disadvantages, which are, one, it's just more expensive to install fiber, and the test equipment is more expensive. It's also more fragile than copper and requires more care in handling. For example, if you disconnect and reconnect a fiber optic, you need to clean it every time. So that's a little different. And you can take copper cables and just throw them around and pretty much get away with it. You can't do that with fiber. You have to be much more careful with handling it. So to carry information on light, we could do it directly through the air. Light beam communications are not incredibly common, but it has been done. I don't know if you can still buy them now, but at one time you could buy laser links for networks where you could have a transmitter on one building and a receiver on another, and you could shoot two laser beams at each other and actually carry information across those laser beams without having any cable. In fact, I have a series of videos where I'm building a laser communicator that is on hiatus at the moment because I just haven't had time to finish it. But it's just something that you could talk into and actually transmit over a laser beam. So not something that's totally unheard of, but it would be better if we could carry that light in a confined place that is protected. And that's where fiber optics come in. And one final thing I want to talk about before I get into the meat of the theories that we need to know is about transmission. The problem is that certain glasses will be transparent to some wavelengths and not others. And there are effects of that. I'm going to put this little chart up here. And we see a couple of lines here. One's this curved line that goes all the way from the left to the right, highest at the left, lowest at the right. And this graph is labeled attenuation. So this is how much loss we have, how much light we lose as it goes through glass. And we see that the biggest problem with attenuation is scattering. So as we get shorter and shorter in wavelengths, we get more scattering. And notice that all these wavelengths are actually in the infrared range. We're not even looking at visible light at this point. And so visible light is scattered so much that we can't really go very far down a fiber optic, so we don't even try to go there. But then we see this other line, which is absorption due to different properties. And we have some spectral absorption, meaning that certain wavelengths are going to be absorbed because of the spectral properties of certain atoms in the glass. And it's not the glass itself, but notice that it says little OH here, meaning OH radicals, oxygen, hydrogen radicals, that are impurities in the glass. And oxygen's going to absorb certain wavelengths and hydrogen's going to absorb other wavelengths. This is related to what I talked about earlier in a previous video about how we can tell what elements are in a galaxy millions of light years away because different atoms dropping their energy are going to do that at different wavelengths. Well, if we have an atom, and there's our Bohr model electron going around the atom, it's a hydrogen atom, and light is coming at us in this direction, so here we are waiting for that light, and it interacts with this electron, it goes into a higher energy state. What's going to happen when it drops that energy? It's going to create a new photon, and our chances of reacting with this photon are different than that one. And so essentially, this photon that was heading right at us is now going some other random direction. It's not the best way to put it to be scientifically accurate, but let's just say the photon was coming at us, it was going to hit us, but then was absorbed and re-emitted and went off in some other direction. That's going to happen at certain wavelengths, depending on what energy levels that electron went between. So if this was hydrogen alpha light, it kicks this up into the third state, drops back down to the second state, emits hydrogen alpha light again. And so we have a whole bunch more of these coming at us, and they get scattered all different directions. That's light that doesn't reach us. So in astronomy, we see dark bands in the spectrum from stars from this scattering. And when it comes to fiber optics, these are wavelengths we can't use because the light is scattered too much or absorbed too much. So this is the absorption spectra caused by the OH radicals in the glass. And then we get down to around 1600 nanometers. We see there that the silicon itself starts absorbing light like crazy. So we only have a narrow range of frequencies where we can use fiber optics. And even in there are a few wavelengths we can't use because of the absorption of OH radicals. So we're only going to use those wavelengths of light that are between these absorption peaks. So let's take a look at how fiber optics operate. And you may know a little bit about this. You've probably heard about it. Fiber optics work by total internal reflection. Let's talk about that for just a moment. Let's say I have a pond and there's water here and there's air above, and I'm going to shine a flashlight from the water, which has a higher index of refraction. The index of refraction is basically the speed that light travels through that medium. So the denser the medium, the slower light travels and the higher the index of refraction. So the water has a high index of refraction, the air has a low index of refraction, and when we are going from a high index of refraction to a low index of refraction, we get a phenomenon called total internal reflection. So let's get these letters out of the way here. And I'm going to shine a flashlight out of the pond. And there's going to be refraction. We've talked about that a little bit. So as the light goes out, it's going to bend a little. And some of it's going to reflect back. So we get some reflection and some refraction as we go from that higher index of refraction to the lower index of refraction. And the lower the angle, let's see if I can get a lower angle here. We're going to get more refraction, and reflection will have the properties we already know about. That reflection is going to be equal on both sides of the vertical line here. But when we're going from a higher index of refraction to a lower index of refraction, there's a phenomenon where we reach what's called a critical angle where, let's do this over here, let's say our light is coming in at this angle, there's our flashlight. 100% of our light is going to be reflected back and nothing escapes. So that is what's called total internal reflection. And it happens when we reach a certain critical angle, which depends on the materials involved. So if we can make a tube of glass such as this, there's the ends, and I shine a light beam in there. If the light beam enters at a high enough angle, a lot of it's going to escape. But if the angle is low enough, 100% of that will just simply reflect back and forth, and it can go down this great distances. And also, if we go around corners, as long as this radius is below a certain radius, that light will continue to reflect inside that. And there was a famous experiment about a little over 100 years ago by a man named Tyndall. Can't think of his first name, but there it is. He took an apparatus where he took a container of water, put a hole in it so there's water flowing out, and he shined a light in there somehow. Maybe he had a little window here or something, and the candle, I don't know, it's before incandescent lights. But he got a light beam going in there, and it followed that water and splashed out. You can look on YouTube and you can see a number of videos of people repeating this experiment. And so that is one of the earliest experiments that showed the principle of fiber optics and total internal reflection, was how that light beam followed that curved path of the water coming out of that vessel. So that is the classic definition of how fiber optics work. That's total internal reflection. However, modern fiber optics rarely use that. If you have plastic fiber such as the SPDIF cable in your audio system, if those are even used anymore, that's probably going to use that principle. We just have a fiber of plastic, and it can guide the light through a path from one component to the other. But other than that, there's not much application for fiber optics that use total internal reflection. So let's take a look at the other ways that light propagates through a fiber optic cable. First of all, let's take a look at the construction of a modern fiber optic cable. We're going to start with 2 layers of glass. Now, we don't need the 2 layers. I'm just going to start out with 1 layer of glass like we did before, and we're going to get our total internal reflection. I'll stop there. But there's a problem with that. What if you touch it and get a fingerprint on it? That's going to change the properties at that point there, and some of the light's going to scatter out, or it can get damaged, or all kinds of things can happen to that. So it's not very well controlled if we just simply have a single glass fiber. So what we do with modern fiber optics is we have 2 layers. We have a core, which has a higher index of refraction than the outer layer, which is called the cladding. So there's the core, and then the cladding. And they say that the purpose of the cladding is to keep the light confined in the core. Well, it does, but that's not the purpose, because we don't need that cladding. The air can act as cladding. So we have the cladding there really to protect the core and to control the properties. So we have a higher index of refraction and a lower index of refraction, and the cladding protects the core so that we have controlled propagation. But there's a problem. The problem is that some of this light, let's get rid of our words here. Let's say we have one beam of light coming in at this angle, and it's within the critical angle, so we get our total internal reflection, and there's our path of light going down the core of the fiber optic. But now let's say we have another one coming in at this angle. Do you see the problem here? The one coming in at the higher angle has a longer path to go down the fiber than the one coming in at a shallower angle. And so we have a problem here. Let's say we send a pulse of light through, and what we want on the other end is the identical pulse coming out. But I like to relate this to perhaps a car race, whether it's NASCAR, F1, Indy cars, or whatever. Let's say, for example, we start out with a 30-car pack of cars, or a platoon, as a traffic engineer would call it. And they're going around the track, and we can see there's our platoon of cars. So let's just draw a few dots here. And there's the start, there's the end. They go by, we know where that platoon of cars is. So there's our pulse coming in. But as the race goes on, some cars are going to pull ahead, some cars are going to fall behind, and that platoon is going to get kind of stretched out. So instead of getting to, here's the cars, there's the cars, or not, now we get sort of a, well, there's some cars, there's most cars, and then there's some stragglers in the back. So we get a little bit of a lessening of that pulse there. But we can still pick that out. But what happens as the race continues to go on? So here's our racetrack. We'll just make it a simple oval here. And eventually we have the cars simply scattered all along that track. Where does the platoon start and where does it end? Some cars have even lapped other cars, so they're overlapping now. You can't tell where one begins and the other one ends, and so we just don't have a signal anymore if we relate that to the rays of light coming through the channel. So we need to mitigate that. And one way to mitigate it is to simply make the core smaller. So let's make the core a little smaller. Small core, keep our cladding the same size. And so we don't have as many paths. And by the way, those paths are called modes. So we call this fiber where we can have these multiple paths in there, multi-mode fiber. And so with the smaller core, there's not as much difference in what those modes are, what those paths are, so we mitigate somewhat. So let's make that core diameter something like maybe 8 times the wavelength of the light. And wavelength is something we didn't talk about in AC because it's not relevant, but it is to communications. The wavelength is going to be the distance between the electromagnetic pulses as they travel through. It's basically the speed of light divided by the frequency, but we're not going to get into that. But anyway, 1,000 nanometers. So at 1,000 nanometers, that's 0.000001 meters, or 1 micron, 1 micrometer. Now let's make this core 0.000008 meters, or 8 microns. So our core is 8 microns in diameter, about 8 times the wavelength of light. And we get a whole new phenomenon when this happens. Now, what happens is that the energy begins to travel down the fiber as an interaction between the core cladding interface. And we do not have any more of these reflection modes or these paths down the fiber. We have simply one. This is called waveguide mode propagation. And so there's only one mode, or one possible path. So we no longer have the problem that we had with multi-mode fiber, where we have some light taking a long path, some light taking a shorter path, and we get modal dispersion, as it's called, because of the multi-mode fiber. So that's one way to mitigate the modal dispersion, is to use what's called single-mode fiber, which once again we have a very tiny core, so that the light energy follows along the core cladding interface, and that's why we call it a waveguide. It works just like a radio waveguide, which we'll talk about down the road in communications. But there's yet another way to mitigate it, which is a compromise between the two. So I'm going to start out with a chunk of glass. Let's make a glass tube of 1 index of refraction. But what I'm going to do is now put that in a chamber, and I'm going to put in some gases in there. I think they're germanium tetrafluoride and silicon tetrafluoride gases, and they're going to go in here and they're going to deposit a soot on the side. And then I'm going to heat it up and I'm going to melt that soot and it becomes pure germanium oxide and silicon oxide of the right proportion. But I'm going to have that first set of gases give me a little higher index of refraction. And I'm going to do that again and again so that my index of refraction starts out low and gets higher and higher. I don't know how to illustrate this, but low index of refraction, higher, 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 and of course in the middle it's the highest index of refraction. As I go to the outside I get lower index of refraction, and then I heat it up and collapse it to make sure there's no air in there, and then I stretch this out for who knows how long, and I now have a fiber optic where the core has a higher index of refraction in the middle and a lower index of refraction around the edge. So what's that going to do? Here in Southern California, we have a phenomenon in this time of year. It's December, usually starts around late August or September and goes on into almost January. And we call this Santa Ana winds. What we get is a high pressure area over the Great Basin area, and that causes a clockwise circulation in the winds. And us down here in Southern California get these easterly or northerly winds coming down. And living near the coast like I do, they come down the coastal range and the transverse range of mountains. And as that air comes down, it heats up. Now, in the early fall, we get our hottest and driest days of the year during the Santa Anas, but as the year goes on, it gets into winter, they can be actually pretty cold. But they're warmer than the air in the valleys. So what we get is a layer of cold air in the valleys. So here's our mountains, and here's the coastal valleys, in which I am in one. And we get these layers of cold air with this katabatic air coming downslope, being warmed up a little warmer above it. So we have the cold air and the warmer air. And I can walk outside and I can tell you, we're having a Santa Ana today, because not only is it crystal clear skies, but I can hear the cars on the freeway a couple of miles away, and I don't normally hear them. Why is that? Because out here on the freeway, all the cars and trucks and everything are going back and forth, and the sound is going like that. And not very much of it reaches me. Normally, it just dissipates. But when I have that warmer air on top, this sound on top, I'm going to use my pin as an indicator. Remember what happens, it's going to speed up in the warmer air. And so this is going faster than that. And so it hits that warmer air, and it is going to pivot right back down. So that sound comes right back down, and so I can hear those cars in the freeway a little bit away. Now, I had a friend ask me once who lived up on a hill. He said, it's really funny. When we're not having a Santa Ana, I can hear the cars in the freeway, but when we are having a Santa Ana, I can't hear them. Just the opposite of what I get down in the valley here. And that is because, of course, normally the sound goes up and he hears it. But now the sound is being refracted back down and he doesn't hear it, so he gets just the opposite effect. What's this got to do with fiber optics? Highest index of refraction, lower index of refraction. So we go from a higher index of refraction to a lower index. We're going to get that bending effect where the sound is going to be curved back in. So graded index fiber optics use that same phenomenon with light. Let's draw that core out as a bigger size here. So let's send a light ray in. As it goes in, what's going to happen? As that light wave comes in, now notice that this is a lower index of refraction here and a higher index of refraction there. So the light is going to travel faster on this side of the wave and slower on that side. So it's going to pivot. And it's going to go down like this, and it's going to pivot back again as it goes back and forth. And it never reaches the core cladding interface and just simply goes down in a serpentine path. So that actually confines the modes to a smaller area. So it's a lot like making a smaller core, but this keeps the waves near the center. And so this also mitigates the modal dispersion that we already talked about, and this is called graded index. So we have step index, which goes one index of refraction, lower index of refraction for the cladding in the core. Graded index means that the core has a high index of refraction in the middle, lower and lower and lower toward the edge, and then finally a cladding of a much lower index of refraction to make sure that any light that does manage to hit the edge reflects back in. So that is called graded index fiber. That's probably the most common type of fiber you're going to encounter in a data center if you find yourself in there. Now when it comes to single mode fiber, you're more likely to find that outside plant going great distances. So your multi-mode fiber, which is either step index or graded index, modern fibers are all graded index. You're going to find in data centers, you're going to find that multi-mode fiber, and you'll notice that your cables are either orange or aqua in color. I'll talk about what that means later, but all your multi-mode fiber is going to be the orange or aqua depending on the type. And your single mode fiber is going to be yellow. So that's one way you can tell them apart is from the jacket color. Okay, so that's the basic idea of what is going on in the fiber. Let's look at some cable construction for a moment because we'll be looking at that down the road. So real quickly, we already started out that our fiber is going to have a core. That's going to be the graded index, step index, or multi-mode, single mode, whatever. There's going to be a cladding around that. Your typical core sizes and single mode fiber, 8 or 9 microns. Your cladding is typically 125 microns regardless of the core. So 8 microns for single mode, bigger for multi-mode. Your multi-mode fibers tend to have a core of around 50 microns or 62.5 microns, rarely larger. Those are the sizes I see most often specified. In fact, if you look at the cable, somewhere you'll see something like 62.5/125. What do you think those numbers are? That's the core size and the cladding size. I saw a cable, I was in a thrift store and I found a piece of fiber optic cable and the numbers didn't make sense here, so I'm not even going to talk about that. But that's something typical. Or if you see 8/125, what do you have? You know you've got single mode fiber. And most fibers are going to be graded index, so they don't need to specify that on the jacket. Okay, so there's your core and your cladding. And then around that there's going to be what's called the buffer. So there's going to be a primary buffer, which is usually a clear plastic, clear acrylic. And that is usually twice the size of the cladding. So it's going to be 250 microns. So whatever the size the core is, 125 microns for the glass cladding. And remember, they're one piece of glass, so you don't separate them. Around that is a plastic buffer to protect it, which is 250 microns. And this is your basic fiber optic. When we talk about what's called loose tube fibers, that's what's in there, is 250 microns. Core, cladding, clear buffer, sometimes it's colored, but it's typically translucent, of 250 microns. And if you're working with, like I said, what's called loose tube fiber, you'll have these fibers in a little buffer tube. Or ribbon fiber, they put these and lay them out on a ribbon and bond them together, and they're typically your 250 micron fibers. But the next type of fiber you may encounter, which is probably most common, is going to have another buffer called the secondary buffer, and it's much bigger, typically 900 microns, made of polyvinyl chloride usually. And so that would be what's called tight buffered cable. So you have the core, the cladding, that's your glass, your acrylic primary buffer, your PVC secondary buffer. That's what's called tight buffered fiber, and they're all bonded together rather tightly. Okay, so now we've got that established. We've got to our tight buffered fiber, so I'm just going to make that this big. And so that's going to be core, cladding, and your two buffers, about 900 microns in diameter. And then around that we're going to have what's called the strength member, which is going to be Kevlar fibers, or aramid. Kevlar is a trade name of DuPont. Aramid is the generic name. There's going to be this bright yellow cord that's inside. So here's your strength member, and then around that is going to be your jacket, which will be colored according to the type of fiber, usually orange or aqua for graded index multi-mode fiber, or yellow for single mode fiber. And other cables, all bets are off, but when it comes to our tight buffered simplex or duplex cable, the jacket color tells you what it is. And I talked about some other configurations. Loose tube fiber, we cut down all the way to that 250 micron diameter fiber with just the acrylic buffer that's somewhat translucent, very tiny. Those are bundled in a pack in a what's called a buffer tube that's called loose tube fiber. And you may find that your loose tube fiber, here's your buffer tube with your little tiny fibers sticking out, and there'll be some Kevlar around that, and then a jacket around that. And so that's your loose tube with your loose 250 micron fibers inside there. And the next one we talked about was the tight buffered fiber, which is going to be such as, here's our jacket, our Kevlar, and then a single 900 micron buffered fiber. So our secondary buffer of 900 microns. Then inside that, if we strip back that secondary buffer, is our 250 micron buffer. And then we strip that, we have our little 125 micron fiber. And typically when we're working with this, if you happen to ever hand terminate it, you're going to want to strip off all the buffer, leaving just the glass fiber. So when you strip it, make sure you get both the secondary buffer, which is the big heavy PVC, well, heavy as far as 900 microns is concerned, which is about a millimeter, and then make sure you're down all the way to the glass. So that's going to be what's called your tight buffered fiber, and it comes with one fiber coming through, or sometimes they're bonded together to make zip cord or duplex cables, so you have transmit and receive. Another type of cable you might see is going to once again have that tight buffered fiber, but instead of just having one, there's a ton of them. So I'm drawing these kind of big. Remember, these are 900 microns, about a millimeter in diameter, so you have a whole bunch of these all packed together. And so if you have one fiber in there, it's called simplex cable, but if you have a whole bunch of them, it's called either tight pack or distribution cable. But if we take that and have just go back to our simplex cable, so there's our Kevlar coming out of our jacket, and a single fiber, which is about a millimeter. If we take a whole bunch of those in a bundle, so what's the difference here? One millimeter or 900 micron, just under a millimeter diameter fibers, each with their own individual jacket. Here we have a whole bunch of those fibers all in one jacket. That's distribution. This is called breakout. Let's put that in its cable with another strength member around it. So distribution, a whole bunch of 1 millimeter, 900 micron fibers. Breakout, a whole bunch of those, but each one has its own individual strength member and jacket. Let's go through the progression here. Simplex cable. A single jacket, Kevlar, and one 900 micron, just under 1 millimeter plastic coated fiber. You take the same simplex cable, but you put a bunch of these 900 micron fibers, you have distribution cable. But then if you take a bunch of these simplex cables and bundle them together, you have breakout cable. And then once again, if we have two of these simplex cables, bonded together, what's that? Duplex. So those are the cables you might encounter as a technician. More to know about this if you're a fiber optic technician, but as an electronics technician, I've covered just about all you need to know about that. So moving right along, we have some other types of cables to talk about. One pair of types get confused somewhat, and that is hybrid and composite. And the meaning has kind of changed and swapped and everything, but it seems that it's settled that this is what it means. Hybrid cable simply means a combination of single mode plus multi-mode cables in one pack. So you have multiple fiber cables in one cable. If some of those are single mode and some of those are multi-mode, that is hybrid. Composite is going to be a combination of fiber, optical fibers, plus electrical connections of some sort. So we might have coaxial cable, might be power cables, might be both. So composite cable is going to be not just fiber, but other types of cables. Hybrid cable is going to be all fiber, but some single mode and some is multi-mode. Okay, just before we go on to the next thing, well, actually the next thing is a little bit to know about installation. So if you happen to have to help install some of these cables, what you need to know is you're going to possibly be pulling cables through conduit. And if you do, you need to use lubrication. You don't want to put too much stress on those cables. You want to limit the stress. There's a lot more to know about this, but just real quickly, limit the stress. There's different ways to do it, such as measuring how much pull you're doing on it, or having devices that will break away if you pull too hard. But the most important thing is you don't pull by the fiber, you pull by the strength member, which may be the jacket depending on the type of cable you're pulling. So if we need to pull a distribution cable through, we're going to want to strip it back so we can get a good hold of that Kevlar that's surrounding all those fibers and put it onto our pulling apparatus and pull by that Kevlar. We also want to be able to pull the jacket along with it, but we want our main pull to be on the Kevlar itself. We have this thing called a Kellam's grip, which is basically a wire version of those little Chinese finger things. You stick your fingers in, you can't get them out, and they put that to hold onto the jacket, but then the main pulling is actually pulling on the strength member of the fiber. And when you're pulling it, you don't want to pull around sharp corners. The rule of thumb is do not pull it around a corner that's any tighter than 20 times the diameter of the cable. Once the cable's installed, then you can have tighter turns. Once it's installed, you want bend radii no less than 10 times the diameter of the cable. Okay, some of the things you might see on the cable. I'm just going to decipher this real quickly. You might see on your cable all sorts of information. And one of them might say something like OFNR. What does that mean? That's easy to figure out there. OF, optical fiber. So let's put these up here as we go across them. OF is optical fiber. N means non-conductive, so there's nothing conductive in there. But C, so OFC, means there's something conductive in there. It might be a jacket, might be copper cables to carry data, might be coaxial cables, might be power cables, but there's something conductive in there. And if appropriate, that conductive cable needs to be grounded. So if it's conductive because it has a metal shield, that metal shield must be grounded. P means plenum cable. This is your more expensive cable that can be used anywhere. The main thing is plenum cable can be used above false ceilings and below false floors where there might be air handling or air circulation issues. Plenum cable is made fire retardant, plus if it does burn, if it is melted and burned, it will not produce toxic gases. And so under the floors where there might be ventilation, above false ceilings where there might be ventilation, and plenum cable, you can actually pull through your ventilation ducts. That's the best way to get your fiber from point A to B. Pull it through your ducts. You can do that with plenum cable. The other one, which is riser cable, you can use it inside walls if it's vertical, but you can't use it across false ceilings or below false floors. And you can use it out in the open. But if you want to be sure you're installing anywhere you want to, make sure you make plenum cable, because that can be installed vertically, horizontally, air handling areas, wherever you want to, where riser cable cannot be installed everywhere. So plenum cable is more expensive, but it's more versatile than riser cable. Okay, let's take a look at some of the designations you might hear about, and some you may not. The earlier fibers, which have orange jackets, are OM1 and OM2. OM1 has a core and cladding size of 62.5 over 125, but OM2 has a core of 50 microns over 125. So remember, this is your core diameter, that's your total fiber diameter or the cladding diameter. So these are both graded index and they have orange jackets, and they're pretty common, but what's becoming much more common is OM3 and OM4, which are laser optimized. So let's back up a little bit. These both have 50 micron cores, but the OM4 is newer and has much better characteristics for both bandwidth and distance. So if I look here, the OM3, you're good for 300 meters at 10 gigabits per second, but the OM4 is good for 400 meters at 40 gigabits per second. So OM4 is the newer stuff and is better. How do you tell them apart? It's rather difficult because they look the same. These both have aqua jackets. So these are orange. These two are aqua. And you have to read carefully to know which is OM3 and which is OM4 if that's important to you as a technician, probably not. But you have to look carefully on the jacket and you still might not find any indication. I think there might be purple markings on the OM4 somewhere. Maybe, maybe not. Might be purple ink, might not be, might be a purple marking somewhere else. But the only way to know for sure is to look at the invoice for the spool it came on. So it's hard to tell these apart just looking at the fiber, but they are both aqua in color, which as I find myself looking at data centers, big and small, this seems to be the most common I'm starting to see around is the OM3, OM4. And the difference is this is laser optimized, where this is not. So why lasers? We get back to that dispersion. If we use LEDs, they have a wider bandwidth than a laser. So let's say we have an LED that has a wavelength of 850 nanometers, which is typical, which is once again in the infrared range, but you actually can see it. It's going to have a lot of light at that 850 nanometers, but it's going to have light, if I can draw this, higher and lower wavelengths. What's that going to do? Well, the different wavelengths travel at different speeds. Now we've got the same problem again we had with the race car problem. Some of those rays are going to arrive earlier and some are going to arrive later, and the further we go, the more that difference becomes. And so if we're using LEDs, we get what's called chromatic dispersion. The colors travel at different speeds, and eventually our pulse becomes spread out to where we can't tell where one pulse begins and the other one ends. So that's the problem with LEDs. Lasers are much better. So we're going to have much less bandwidth on the laser, and so therefore we have less chromatic dispersion. So the idea to get our least dispersion is to eliminate our chromatic dispersion by using lasers and to decrease our modal dispersion by using either single mode fiber or graded index multimode fiber. And so that's what we're doing to get the greatest distance out of our system. So aqua is OM3 or OM4 laser optimized. Orange is OM1 or OM2, which is not laser optimized. Here we use LEDs for the light source. Here we use lasers for the light source. Now we're going to take a look at connectors. I'll throw some pictures up here because it's really hard to draw them. I don't know why I'm showing this connector. I just am. It's kind of obsolete. I haven't seen this in an actual installation ever. I've teach people how to make them. But here you go. This is the ST connector, which is a bayonet type connector. It's modeled after the B and C connector where you push on, turn, and connect it. But what's the most popular connector I've seen, and from what I can research is the most popular connector, is the subscriber connector or the SC connector. And this is just a square connector, and it's just a push in, pull out type of connector. And another one that's I don't see very often, but apparently is common, is the LC or lucent connector, which is much smaller and has a much smaller ferrule. So if we look at the connector, so here's the main body of the connector, and there's a little thing that sticks out, and the fiber is right down the middle of that, and that's called the ferrule that connects to that protects the fiber. And so that's usually made of zirconium ceramic material of some sort. It's white, very fine ceramic material. And the fiber is right down the middle. And so when you're putting these connectors on, you want to make sure you only have the glass, get all those buffers off, because that's just big enough to get the glass in there. And on the LC connector, it's much smaller than on the other connectors. And another connector we have is the MTRJ. That stands for multiple termination, I believe. RJ comes from its resemblance to the RJ45 connector. This is typically used for duplex connections, so there's actually two fibers in here. Plug it in, and so you get both transmit and receive, unlike the SC connector, where sometimes you'll find those connected together, two SC connectors with a clip, and you use them both at the same time, or they have to be used one at a time. The MTRJ, two fibers, transmit and receive, one connector, click it in. Actually never seen this in the wild, but apparently it's popular, so I added it to here. And then another one, the MPO, which is a multi-fiber push-on, also called the MTP, which is a trademark name for the same thing, and it's used for ribbon cables. So one connector and a whole bunch of fibers in a ribbon for the MPO or MTP connector. And another thing about the connector is color. If the connector is blue, it's single mode fiber. If it's beige, it's multi-mode fiber. And if it's green, it's APC or angled physical contact. So what we want to do is get two connectors together. So whenever we're connecting two fibers, whether it's two connectors, or this might be the receptacle in a switch or something, we want to get the two ferrules to connect straight to each other. And there's a little bit of a curve to it. It's getting a little scientific here, but the ferrules have a slight curve. And the idea is that curve is just enough that, yes, there's a little bit of give. You push them together, it pushes those fibers together, and they go into what's called optical contact. This is something that happens if a surface is very highly polished. They almost become one piece of material. And so there's very, very little reflection between the two. I had a story, a friend of mine who used to be an optical technician was working with some optical flats, and the way you test it is you have a test flat, so it's just the little disc of glass that's perfectly flat, no coating, and you take the flat you're making and you put it on top of there, and when they come together, there's going to be light coming in, there's an interference pattern, and if the lines are straight, then you know that they match. But if you see curves, you know they don't match. But what he saw, he put it down, he saw those interference patterns go zoop, and he heard a click. They went into optical contact, and he could not get them apart. They were basically now one piece of glass. Since they were different types of glass, he was able to put them in an oven and heat them, and because of the differential expansion, he was able to get them apart. But he almost ended up with a piece of scrap because of this optical contact. Well, that's basically what they're trying to do with fiber optics, is get those two fibers in optical contact, and so they have just the right curve of that ferrule to get those two pieces of glass to come together, and the force flattens them out, and they go into optical contact if you have a really good polish on them. And so that's the idea, is to get that optical contact, and that's called ultra physical contact, or UPC. But there's still a problem. We can't get rid of the reflections that we're going to have at this interface entirely, but we do a pretty good job with the UPC. But there's another one called APC, where these ferrules are polished. I'm going to exaggerate this, of course, here. More angled. And that angle is 8 degrees. So that's APC. And what that does is when they come into contact, any light hitting here, if it goes through, it goes through. But if it reflects at an angle high enough that it's greater than the critical angle, and out it goes and doesn't reflect back through the fiber. So that's what an APC connector is, and that is green. Okay, now I don't know if as an electronics technician you're ever going to put connectors on cables or splice them, but we'll talk a little bit about that. You know, in my fiber optics class, I taught people how to put fibers into connectors and how to test them, because employers expected them to know how to do it, but then they get on the job, they never do that, because you buy pre-terminated pigtails, as they're called. So you have a fiber already on the connector, so you either have a patch cable or a pigtail has a connector on one end, the other end is open that you can splice onto another cable. But anyway, we're not going to talk about making the connectors. That's for the fiber optics class. But we'll talk about splicing real quickly. There's two types of splices. There's a butt splice, where basically the fiber optics are put into a tube and butted together. And then we crimp them in there, and that is a butt splice. But a better splice is a fusion splice, where we take the two fibers, we cleave them off, so we don't have to go through any polishing step. As a matter of fact, even with the butt splice, we don't really polish them, we cleave them. What we do is we have the fiber, we want to make a surface to go into the splice, so we scratch it with a device that puts a little bit of a scratch in it, and then we give it a little bend, and it just snaps right off like cutting glass. And if it's done right, we get a perfectly flat surface that doesn't need to be polished, and we put those together. And same thing with a fusion splice, but instead of butting them together and crimping them, we put it into a device that has a couple of electrodes, if I can draw them here, and we get them to just the right distance, not quite touching, there's a just right distance. And this is all done by machine now. In my class, I had a fusion splicer where we did it by hand because I wanted them to learn the nuances of it. But then we showed them how modern fusion splicer, where it's all done by the machine. You cleave it, stick it in, and press a button. But anyway, it moves them to just the right distance, aligns them, and then with them just the right distance, it puts a high voltage across these two electrodes. And if you have a microscope where you can watch it, you can see the little zap. That's why I like the little hand splicer I had. It had a microscope where you could actually watch the fusion happening. Modern ones use cameras. So the camera's overwhelmed by the brightness, so you don't get to see anything. But anyway, that spark melts the glass and it fuses together, and you have a slight little dip, but it's calculated to be just right. That's obviously exaggerated. And you end up now with one piece of glass, and so there's no possibility of reflection. So that's what a fusion splice is. So most likely, if you work with fiber optics, you're going to do fusion splicing, but the splicers are started around $10,000 or something like that, so it's pretty expensive. So if you need to do a few splices, you might want to use butt splices. You can buy them for a couple of bucks each. But if you're going to do a lot of splices, of course, you're going to use a fusion splicer. And then, of course, after it's spliced, you put some protective jackets on it. And if you're going to splice ribbon cable, you can do them one at a time by hand, right? No, a mass fusion splicer puts all those ribbons together, flashes a little spark across these to clean it up. You push the button, whether it's a single splice or a mass fusion splice, it'll zap that to clean up any garbage, and then it'll fuse them together. And so a mass fusion splicer will fuse ribbon cables together. So that's how cables are spliced. Cleaning, basically you use lint-free pads and isopropyl alcohol or some other cleaner that's made for fiber optics. There are also other fiber optic cleaning things. Some of them are little sticky things where you uncover some pads. You just go, hope that little sticky thing will take any debris off of the fiber. There are little fiber optic cleaning things. It's like a cassette with a tape on it, and you pull a trigger, it exposes the tape, you clean the fiber, let go of the trigger, and it advances the tape and covers it up. What you don't do is you don't, no, we don't clean fibers that way. Yeah, we don't want any debris of any kind on these fibers because we've got a very, very tiny light channel. That core is very tiny, and a little piece of dirt, debris, dust, smoke, or whatever is going to block that if we get it in there. So we have to be very clean when we work with these. One of the things we teach is that you don't use fusion splicers in manholes. So if you're down in a manhole doing some splicing, which you're probably not going to be doing as an electronics technician, but you might find yourself down there with the guy working with one. And no, you don't use them in manholes because gases can get in there from nearby sewer lines that can be explosive. And sort of reminds me of the guy who was skydiving, and he jumps out of the plane. He pulls his ripcord. These days, I guess they tossed their little pilot chute, and the parachute didn't come out. And couldn't get out, so he just no problem. Rolls over, pulls the handle on his reserve chute, and nothing happens. So he's falling down there trying to contemplate what to do next, and he looks down and he sees a man coming up from the ground at him. He's falling down, this other man is coming up. And so as he passes, he says, "I'm skydiving, what's happening to you?" And he says, "I'm lighting a Coleman stove." Where are we going now? Testing. Okay, different ways to test fiber optics. Let's say you have a dead fiber. You suspect it might be broken. You can use what's called a visual fault locator. And this is basically a laser pointer, except it has a lens that focuses the light right on the core of the fiber. So there's your ferrule, your fibers right in there, and we have basically a laser with a lens that focuses right on there. I tried this with a laser pointer. It doesn't work. You have to get that light focused in there properly. And you get that visual laser, usually red laser. I've never seen a green one, but could be. You get that red laser going through there, and if there's any break in the fiber, you look along the fiber and there's a bunch of light leaking out right here. That's where your break is. And you can also, just to show that it happens, you can wrap that fiber around your finger and it'll light up because you're getting too small of a turn, and the light now no longer goes through at the critical angle and starts to escape from the fiber. So in fact, there are ways to get information out of a fiber that hooks onto it and bends it so that the light comes out in a little photodiode that can read the light in the fiber without being at either end or without breaking it. So that's a visual fault locator, just basically a little laser. As an electronics technician, you're probably not going to be testing fibers, but you might. So there's a kit called an optical loss test kit, and basically put the diagram of it up here. So we have a light source over here somewhere. We have what's called the launch cable, which is just a patch cable that goes to a two-way connector called a barrel connector, and that connects it to the fiber that's being tested somewhere around here. So those little circles are the fiber you're testing. Goes to another barrel connector, to another patch cable, to a power meter. So we have the launch cable, the fiber being tested, and the receive cable. And the power connector measures power in dBm. And if you go back to our talk about decibels. Remember that decibels is always a ratio unless you put a letter after it. dBm means that we are comparing our power to 1 milliwatt. So if we have a power meter, an optical power meter with our fiber coming in it, and it says 0.0 dBm. What's that telling us? Well, it's telling us that power coming in is the same as 1 milliwatt. There's no difference between 1 milliwatt and that power. So 0 dBm equals 1 milliwatt. Now what happens if I see minus 3 dBm? Well, 3 dB is a ratio of 2 to 1, so if we're cutting that in half, I have 0.5 milliwatts. So see how that works? So positive 3 dBm is what? 2 milliwatts. So 3 dB is a doubling or a halving. 0 dBm equals 1 milliwatt. Anything less is less than a milliwatt. Anything more is more than a milliwatt. And so what you're going to do when you're testing a cable is first you're going to put that launch and receive cable together and get a baseline reading. And so your power meter says minus 20 dBm. I don't think that's an unreasonable number for the amount of power from the light source. And so now you've got the launch and receive cable together. You've got your baseline measurement. You pull those apart, put in your cable being tested, and now the meter says minus 23 dBm. What's that telling you? How much loss do you have in dB? Well, if you start with minus 20 with the cable not in there, and you put your test cable in there, now you're losing 3 dB, go from minus 20 to minus 23. What is your loss? Ain't that easy? No calculations from watts to dB. You just take the difference between your two dBm measurements, and that's your loss in decibels. A typical link loss budget, which means the amount of loss they can allow in a whole set of splices and connectors and whatever between 2 points, is typically around 20 dB. So we can have down to minus 40 dB on a long cable with lots of splices and connectors and still be within our budget, which is calculated when you make the installation. So another thing that you might hear about or see, who knows, is the OTDR, the Optical Time Domain Reflectometer. Ooh, fancy word for this device. It's basically radar that sends down, maybe LiDAR if you want to be correct, sends a pulse of light, laser light presumably, down the fiber. So here's our OTDR. We connect a fiber to it and it goes wherever it goes, and we have a display on it. And I used to like to use one that was an old analog one with the CRT display, because once again you get a feel for what it's telling you. And then we would give them a more modern one which gives a digital display. But anyway, what it's going to do is send a pulse of light. So the light here turns on, the light turns off, and there's that pulse of light, and it's going to start traveling down the fiber. Now as it travels down the fiber, some of that light is going to be scattered back. And so that light comes back in. And so we turn the light on, turn the light off, and then we watch for what comes back. And so while that light is on, we can't see anything. So let's go ahead and kind of draw what I'm going to put up here. Just draw it by hand here. Here's our distance scale. It's basically a time scale, but we know how fast the light is traveling through the fiber. We have to set up the OTDR for the particular index of refraction of the fiber we have, if we can find it. That might be in the invoice, might be in specifications at the manufacturer. It's a little hard to find, but it's typically going to be about 1.5. And then here is our reflected power. They label it as attenuation, but it's really reflected power. But since they label it attenuation, I'll do the same thing. But basically it's telling you how much power is coming back. So when it turns on that laser, we get a lot of reflection back, so a lot of power coming back, but then we turn it off and we start watching for what comes as that pulse of light travels down the cable. So this is all happening very quickly. That light is traveling at perhaps 2/3 the speed of light in a vacuum. So it's going down very quickly, but we have this high-speed equipment that we can see what's going on. So the initial pulse, can't see what's going on because we're getting all that reflection back. We turn that off, and now we just see what's coming back as that pulse goes down the fiber. And so as it goes down, we see so much power coming back, but that power is attenuated as it goes down, so it gets less and less and less. So we see that our reflected power goes down with time, which equals distance because we know that how fast that light is traveling. So let's say we hit a fusion splice. That splice is not going to have any back reflection, but we are going to lose power there. And so we're going to see a little dip. So if you see a dip, what's that? That's a splice. But now we get to a point where we get a reflection. So all we're getting is backscatter, 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 but now we hit an interface between two fibers at a connector, and we're going to get some back reflection. So we get a spike, and then when it finishes reflecting, oh, it's gone down even more. So that's a connector. And then we finally reach the end of the cable. Well, that end of the cable is going to be a glass to air interface, so we're going to get a Fresnel reflection. And so we get another reflection, and then nothing, and then we just see the noise in the system. So that's the end of the cable. So that's a good cable, good even losses there, not too much loss at the connector, fairly desirable. If we see the cable goes, let's see, there's our initial pulse, and it goes so far, and we get a spike and then noise. That looks like a break in the cable to me. If we're going down, and we get a spike and a lot of loss, that's possibly a break in the cable where some light is getting through, but more likely as a cruddy connector, maybe a connector that needs to be cleaned or redone or something like that. So that's just a little bit about what the OTDR can tell us. It can tell us how much loss we have, but it's not as good as a source and meter to test. So if you're testing for actual optical loss, you need to do the source and meter. The OTDR is really for fault finding to make sure that everything looks good. So you get your installation, you stick the OTDR on each cable, see a good connection on each one, not too much loss at our splices and connectors, we have a good to go installation. So that's the OTDR. So finally, safety. You're going to be, if you are a fiber optics technician, which I'm presuming you're not because this is for electronics, but you still might do some cleaning, you might work with some hazardous chemicals like isopropyl alcohol. Well, take proper safety precautions with whatever chemicals you might be using. You might be using other cleaners. Be sure you understand the safety aspects of it. But another thing to remember is that what are we shining down this fiber optic? Often it's not lasers. What color are those lasers? Infrared. You probably can't see them. If it's 850 nanometers, yeah, you can see that. But 1,000 nanometers, forget it. So I don't see anything in this cable. I don't see anything anywhere now. So you want to be careful about that. Remember that you're working with lasers. Don't be using a microscope. That's another thing I probably won't be using, but technicians will. They can stick a connector in a microscope and say, oh yeah, that's a good clean, that's a filthy dirty connector or whatever it is, or somebody didn't even polish off the glue or whatever. Don't be putting connectors up to your eye through the microscope unless you are absolutely certain that there's no laser light coming through it. So you have to make sure it's shut down, make sure there's no light going in there, and if you pull it out, tag it, make sure the tag says do not plug this in, because that is a safety issue. Now that being said, the lasers used to feed fiber optics are of a low enough power that according to ANSI standards they are not hazardous, but why take a chance? Don't be sticking that up to your eye. So anyway, that's what I think you need to know as an electronics technician about fiber optics. So I hope you found this useful and informative. If you did, please give me the thumbs up down below. That really helps the channel. Don't forget to subscribe and hit that gray bell when you do, so you get notified when I put up new videos. And if you want to learn electronics technology, you can go to Vocademy.net and take my free electronics course. And as of now, I am still avoiding putting commercials on these videos because I'm depending on you to make all this possible. So to help me make these videos and to keep Vocademy free, you can support me by going to patreon.com/Vocademy and pledging your support. Or if you want to make a one-time donation, which I really love it when those come in, you can go to paypal.me/Voced, V-O-C-E-D, and send me a one-time donation. So a big thank you to my patrons and my one-time donors. I could not do this without your support, and thanks to everyone for watching.